Welcome to the first session of our Spring 2022 short course sponsored by NIST, Sampling for Forensic Practitioners. Your presenter today is Dr. Alicia Carriquiry. Dr. Carriquiry is the Distinguished Professor and President's Chair at the Iowa State University Department of Statistics. She's also the co-founder and director of the Center for Statistics and Applications in Forensic Evidence. Dr. Carriquiry, I'll turn it over to you.
We offered this last year for the first time, and the comments that we got were all pretty positive, so thank you very much. The one thing that everybody was hoping for was that I would go a little slower and perhaps add a third session, and that's what we have done this year. So before I get started, just a note to say that this course, like most of the courses we offer here in CSAFE, these are geared to practitioners. And so if you're hoping to learn a whole lot of theory about sampling, this might not be the course for you. Or if you're a statistician that already knows a whole lot about sampling, this is not the course for you, most likely. This is meant for the practitioner that really hasn't had a chance to take a class in sampling. And it's the focus is it's very practical, where this is a very applied course. And in fact, for the third session, what we're going to have is Joe Zemmels, who is one of our research assistants here in CSAFE. He is going to end the course by showing you some Excel programs, how to implement some of the things we're going to be talking about here, about today and next Friday. And so in addition to the theoretical lectures that I'm going to be presenting, Joe is also going to be presenting a practicum that will help you implement some of these things. So without further ado, and if you have any questions, let's see, do I get to see, how did this happen? I didn't want to go there. Did somebody change my slide? Okay, this is what I want. Okay, so without further ado, this is something that made the news back in the I don't remember exactly when this was, but not that many years ago. This were some snippets that appeared in the popular press. 84% of women are not satisfied emotionally. 77% of all women that have been married 5 or more years are having sex outside of marriage. 95% of women report emotional or psychological harassment. These were all snippets that were obtained from a book that was published by somebody called Shia Height. Maybe you remember this book. If you're as old as I am, I do remember this book. It was a revolution. So this book was published and it started this conversation about sex, and the snippets that I just showed you were pretty revolutionary. 95% of women that have been married 5 years or more are having sex outside of marriage. My God, that sounds pretty high. And so as soon as this book was published, criticism started to pour in. And some of the criticisms were pretty beastly. Conclusions are dubious and of limited value. That's okay, but this is the equivalent of medical malpractice in the survey field. This was a particularly biting criticism coming from somebody that was a big guy in the social sciences. And so the question is, was Shia Height right, or were the criticisms fair? And it turns out that there's a little bit of both. So Shia Height was a social researcher at the time. And what she did is she sent out 100,000 or more questionnaires in the hopes of getting response from women and allowing women to speak up and tell their story. So what she did is she sent this 100,000 questionnaires to organizations such as Caucus for Women in Statistics, or church organizations for women, or in fact, many of these all women organizations, she got a very low response rate. So even though she got something like 5,000 questionnaires returned, that was only 4.5% of the 100,000 that were sent in. So response rate was pretty low. And to make life even more complicated, the participants, the people that chose to send the responses in, were self-selected. So these were people that decided they were going to be sending their responses in. So what was Height's mistake? Height's mistake was to take the responses from this self-selected sample of respondents and generalize those responses beyond her sample. So the statements she made about 95% of all women married 5 or more years are having sex outside marriage, that makes absolutely no sense. It's well beyond what her data allowed her to say, because the sample on which she based those findings was really not representative of women in the United States at the time. It was only representative of women that participate in this all women organizations. And in fact, not even of those, because only 4.5% of the women that were contacted decided to return a questionnaire. So this was a very non-representative sample of women, and as you can well imagine, those conclusions do not apply widely. So that's what we're going to be talking about in this course. We're going to be talking about how to carry out sampling and collect samples that allow us to generalize the findings and the results that we get, and how to recognize when the sample with which we're working or with which somebody else is working has limitations that do not allow this type of general conclusions that apparently apply to a wider group of individuals. It turns out that you can be dramatically mistaken if your sample is doesn't have the attributes it should have. So here's an outline for the course. We have 3 days. Today, we're going to motivate this idea of sampling. We're going to define terms and try to develop a common vocabulary. We'll talk about the attributes of a good sample, and we'll describe some of the more common sampling methods. On day 2, which is a week from today, we'll talk about what to do with the observations we collect from a sample. So how do we translate samples into inferences about the population from which we drew those samples? And then we're going to spend a fair amount of time talking about sample size calculation. So this is something that, first of all, it's not easy. Second of all, is something that anybody that wants to sample is faced with. How many observations do I have to include in my sample? And that will, of course, depend on the type of inferences you want to make, the type of material you're working with, and several other things. And finally, on day 3, we're going to spend a few minutes talking about the difference between frequentist or classical sampling methods and Bayesian sampling methods. I know that in the forensics world, anything Bayesian is a hot topic these days. So surely you're going to find yourself reading about Bayesian sampling methods. And so we'll talk a little bit about those. A couple of odds and ends, and then Joe will take over and talk to you about how to implement some of the things we learned about in the first 2 days. Joe has developed some programs in Excel that are very simple to use, and that, of course, you can have, and that will allow you to implement some of the things we're talking about here. So, Sampling is all over in the forensics world, I have to tell you, and there is any number of ASTM standards that refer to sampling. Here is one of them. This is ASTM E2548. This is a standard guide for sampling seized drugs for qualitative and quantitative analysis. And I should say that sampling applications often talk about drug seizures, but there's many, we'll give other examples. There's many other applications in which you might want to apply principled sampling methods. Anyway, so what the standard talks about is two types of sampling, statistical, non-statistical. We're going to learn about those. And it talks about when one may be more appropriate than the other. We'll come back, we'll circle back to this standard later in the course, but in principle, everything that we're going to be learning in this course is covered in some of these standards. All right, so why are we interested in sampling? Well, there's many reasons why we might want to draw a sample from some population. Typically, we want to make some inferences. In other words, we want to learn something, say something about the population from which the sample is drawn. And of course, you know, if ideally, if we could measure the attribute that we're interested in every unit in a population, then we wouldn't have to sample. But typically, that is going to be impractical for reasons of time, cost, accessibility to all items in a population, what have you. And so oftentimes, in fact, very often, we have to work with a sample. All right, so, but the idea typically is to learn something about the population from which we drew that sample. And there's different things we might want to learn, so different types of inference. One might be to learn, for example, about some attribute of the population, some quantity in the population. For example, if I'm a DNA analyst, I might want to know what the frequency of a certain allele might be among individuals of Chinese ancestry. Can I use, for example, the same database that I use for, let's say, Caucasians individuals to compare against a genotype of a person of Chinese ancestry, or some gene frequencies different between the two groups? That's one question. What obviously, if I want to do that, I am not going to try to do a genotype analysis of every person in the United States of Chinese ancestry. I might get a sample of individuals of Chinese ancestry and try to understand the allelic frequency in that sample, and then hopefully generalize to the population of persons of Chinese ancestry. Or I may have a very large seizure that contains baggies, apparently full of drugs, and I may ask what is the proportion of those baggies that in fact do contain drugs. Again, I could perhaps analyze every baggie in that seizure, but if that seizure is large, this is not only going to be very costly, it might also increase the risk to the analyst of being exposed to all these drugs. So sampling in this case would be a good way to go. I may want to estimate the association between two or more variables. For example, let's suppose that I have two instruments, one that is extraordinarily expensive to run, but gives me very precise measurements, and another one that's much cheaper to run, but doesn't give me such precise measurements. Can I come up with some sort of a calibration equation to take the cheap measurements and adjust them so that they look like the expensive measurements? Well, this is another sampling question, because of course I have to ask myself, what kind of materials do I need to be, if I want a good calibration equation, what kind of samples do I need to make sure I measure with both instruments and how many, so that I have a reliable calibration equation. And this is for those of you that use instruments in labs. Or for example, and we won't say much about this last motivation, we might want to determine causal effects. For example, if I I'm a lab manager, if I spend money on a certain type of training, will that improve the performance of latent print examiners? So if I want to learn about this cause and effect type of situations, how should I design the sample? How should I design a study so that I can understand the causal relationship between a training program and performance of my examiners? So there's any number of situations where sampling is going to come into play. Sometimes we think of experiments. Experiments are nothing more than a specific type of sampling. So to run an experiment, you have to sample. And so, you know, the ideas that we're going to be presenting here apply very generally, is what I'm trying to say. The type and the quantity of the data that you collect is going to determine your fate. So the type of inferences, the type of information you can glean from your sample is going to depend dramatically on the methods you use to collect the data. And so it's very important to think very carefully about this very first part of your study, the sampling plan, before you go collecting any data, because that's what you're going to have, and that's what's going to determine what kind of information you're going to be able to extract from the data you collected. All right. So what is sampling? So we know, I mean, everybody uses the word sampling, but sampling more formally simply consists in selecting a subset of the items from a population. And here the term population may be a population of persons. It may be the population of baggies in a seizure. It may be the population of guns in the city of Chicago. It might be whatever your target population is. What is the population about which you want to learn something? And so the idea here is, you know, the sample is not the objective here, which the objective is learning about the population. And as I said, ideally, you know, if you have a seizure of baggies with 15 bags, maybe you can analyze the content of each one of the 15 bags, in which case you would not need to sample the bags that will be analyzed. But if your seizure has 200,000 baggies, then you don't want to analyze 200,000 baggies. And so the collecting a sample here becomes a necessity. So you sample, typically we sample because it is too costly or too time consuming to study the entire population. And we'll talk about two major sampling paradigms, what we call probability sampling and what we call non-random sampling. And probability sampling or random sampling is what's going to allow us to make inferences from the sample that generalized beyond the sample items to the population from which we drew those samples. Non-random sampling will not allow us to do that. So, random sampling, the nice thing about random sampling is that we can use the laws of probability. So we have this enormous toolbox that we can use in order to make inferences beyond the sample items. That's not going to be available to us when we do non-random sampling. There's a place for non-random sampling, and we'll talk about, we'll briefly refer to that, but most of the course is going to be focusing on random sampling. All right, so here's a big picture, and we'll come back to this big picture several times. Here's a population. I'm interested in learning something about this population. I am going to use probability theory to draw a sample. from that population, this is my sample, that has certain attributes. I want the sample to have certain attributes that will allow me then to take these sample items and learn something about the population from which the sample was drawn. So probability laws will allow me to pick a random sample that has some good statistical attributes. And once I have that good sample, statistical methods, inferential methods, will allow me to say something about the population from which the sample was drawn. Okay, here's a funny cartoon because there's any number of funny cartoons about surveys. 87% of the 56 who completed more than 23% of the survey thought it was a waste of time. There's several corny cartoons in among the slides, just to make you smile every so often. All right, so here's a very simple illustration of some of the concepts that we're going to be talking about in a minute. Suppose that you're interested in the proportion of cases that arrive in a lab per week that involve firearms. That's that's a question you have. So here the population, let's suppose, is all accredited crime labs in the United States. And I have no idea how many there are of those. For the purposes of this completely invented study, let's suppose there's 100 labs in this population. The unit, what we might call the unit of study, is a single lab. And so the idea here would be you contact a lab, you ask the person in charge of the firearms unit how many firearms cases they get every week. Then you talk to the person in charge of receiving all cases in the lab. You ask that person how many cases does the lab receive on the average every week, and then you compute the proportion of all the cases that involve firearms. And so imagine you ended up with this data. So let's suppose that 5 of the 100 labs get 10% of their cases per week involve firearms. In 8 labs, you have 20% of the cases involving firearms. In 16 labs, you have 30%, and so on and so forth. So this is the real population. And of course, we don't know what this population looks like. This is the unobserved true population values. So the unknown population average, really, if you were to measure all 100 labs, you would find that on the average, 44.6% of all cases in the 100 labs that arrive per week involve firearms in some way or the other. We're going to call this unknown population average. We're going to call it pi. And the idea here is that we're going to try and estimate pi, but using a sample of these 100 labs. So that's the entire idea. So I don't want to bother calling all 100 labs. I'm just going to draw a sample of the 100 labs and call it a day. All right, so this is what we're going to do. So let's suppose that we have a listing of the labs, and I assign a number to each lab, and then I randomly select 5 numbers out of a bag that has 100 balls labeled 1 to 100. I shake the bag and I stick my hand in the bag and I draw 5 balls, and that will give me the 5 labs that will be included in my sample. And so let's suppose that I do what I just said. I contact the firearms examiner, the person in charge of the firearms examining unit, and I say, how many cases do you get per week that involve firearms? And then I contact the lab manager and I say, how many cases a week do you is the intake in your lab? And then I estimate a proportion, call it P, in each lab, which is simply the number of firearms cases divided by the total number of cases. And I average over the 5 labs. And I get an estimate. I'm going to call it pi hat. That's my best guess of this unknown nationwide proportion. And the question, of course, is how good an estimate is this pi hat? Well, unless you get insanely lucky, pi hat is not going to be equal to pi. Why? Because we're we're relying on information from only 5 labs to try to say something about the average number of cases involving firearms in 100 labs. And so you would expect that this pi hat is not going to be identical to pi, but you hope that it might be close. And so, but there's errors that, there's going to be a difference between pi hat and pi. And this difference that we will inevitably have can have 2 sources, 2 types of what we might call errors. One is the type of errors that we call sampling errors, and the other type is what we might call non-sampling errors. The sampling errors, very briefly, and we'll spend a whole lot of time on this, but the sampling errors arise for the obvious, right? We're relying on information from a subset of the population, not from information collected from the entire population. So you would expect that you would have some differences. The non-sampling errors, and we can we'll see how we can address this error and minimize this sampling error. And this is going to have to do with the size of the sample, the sampling design that we use, and several other things. The non-sampling error is the more perverse type of error, because sometimes we don't even know it's there and can really, really screw our inferences. So some of the sources for non-sampling error, and again, we'll talk about this much more in the slides to come, what we might call under or over coverage. So for example, imagine that instead of having a list of all 100 labs, let's suppose that there's 100 accredited labs in the United States, but somebody handed me a list that only includes 80 of those labs. So there's 20 labs that for some reason didn't get on the list. And so that is what we might call under coverage, because my listing, my frame, my population from which I'm going to be drawing the sample is not complete. It excludes some cases that should be included in my list. And so there's some labs, the ones that are not included in my list, that cannot be selected simply because, as far as I'm concerned, they don't exist. Then there's the issue of, and then the overcoverage, as you might imagine, is the other problem. Let's suppose that somebody hands me a list, and instead of having the 100 accredited labs, it has 100 accredited labs plus 10 labs that are fly-by-night operators that that somehow got into that list, but have no accreditation, have no quality control. In fact, should not be on that list. So that is what we might call overcoverage. There's the issue of non-response or incomplete responses. This happens when, for example, I sample, let's say, 10 labs from the list, and I send out the questionnaire to the 10 labs, and I only get back responses from 8 of those 10. That would be non-response. Incomplete response is when you have several questions that you're asking that you're taking several measurements in the units in your sample, and for some reason your measurements are incomplete. So in some units you have complete measurements, in other units you don't. And then there's many other different biases that can creep in. So we'll talk about all of these in much more detail later. So, continuing with our simple illustration, let's suppose that Peter, Paul, and Mary, and again, this is aging me. I wonder how many of you guys remember Peter, Paul, and Mary and Puff the Magic Dragon. Peter, Paul, and Mary have independently decided to draw a sample of 5 labs to estimate the proportion of cases that involve firearms. Remember the pi. And let's suppose that they do this randomly. So they do this well. And actually, I did it randomly. So let's suppose that Peter's sample includes labs number 59, 13, 4, 97, and 10. And Paul's sample includes 5 different labs. And Mary's sample includes this particular labs. And let's further suppose that everybody in each one of these labs responds honestly and accurately. And let's suppose that the estimates that Peter, Paul, and Mary get for pi are 36% using the 5 labs that Peter had, 32% using Paul's labs, and 46% using Mary's labs. Now, you remember the true value in the population was 44.6%. So none of these three are correct. But if you happen to take the average of these three, you would get something that's maybe, maybe 40% or so. And so on the average, if the sample is correct, if the sample is random and unbiased and representative and blah, 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 you would expect that on the average, your estimate should be close to the true value. So in this case, we see that we get 3 different estimates from the 3 different samples. And this is what we talk about when we say that when we mention sampling error or sampling variability. Because you are relying on only 5% of the labs, in this particular case, 5 labs sampled out of a population of 100, you would expect that the value you get from measuring this proportion on only 5% of the labs is going to be different than the one you would get if you had measured the entire population. So if instead of having a sample of size 5, we had taken a sample of size 30 out of the 100 labs, these 3 estimates would have been much closer to each other, and in fact, much closer to 44.6. And so sample size is going to be inversely related to sampling variability. The bigger your sample, the less variable you can expect your estimate to be. Okay, what about non-sampling errors? Well, let's do, for example, 2 sources. Let's say undercoverage and non-response. So undercoverage, like I say, occurs when not all 100 labs are included in the list from which we sample. And I have no idea what the symbol here means. But let's suppose for whatever reason that every lab that had that in real life has a proportion of firearms cases that exceed 80% of all cases, for some reason were excluded from the list I had to sample from. And that's one situation. And the other one is the non-response case. Let's suppose that, again, for whatever reason, some labs did not respond to the survey or to the questions. So here I have Peter, Paul, and Mary. This is the original sample that Peter drew. This is Paul's sample. This is Mary's sample. And these are the percentages in each one of the 5 labs that the original 5 labs that Peter included in his sample, the average of these percentages was 36%. Now let's suppose that there's undercoverage. So this lab was not included. The lab with 97% firearms cases was not included in the list. And so I didn't have a chance to draw this lab. And so instead, Peter drew, all the rest are fine, but instead Peter drew this one lab that had 79% of firearms cases. Look what happened to the estimate. So it went down from 36 to 33%. In the case of non-response, suppose that every lab that had, 85% or more firearms cases decided not to respond for whatever reason. Now I only have 4 labs in Peter's sample, and this one is not available. The 97 is no longer available. And I take the average of these 4, I get 20.1. So in this particular case, the non-response had a dramatic effect on the estimate of the proportion of cases involving firearms. In the case of Paul, we don't have any differences because the undercoverage, Paul would not have been affected by undercoverage, nor would have been affected by the non-response, because in Paul's case, none of his original labs fell into any of those 2 categories. So Paul is golden. Mary, again, has an issue because this were her original lab, or these were the percentages in her original labs. Well, if in the case of undercoverage, this lab is not on my list and this lab is not on my list anymore. So let's suppose that instead of these two labs, Mary had sampled this lab with 67% and this other lab with 43%. Look what happened to her 46%. It went down to 32%. That's because the list did not provide a chance for labs with very high percentage of firearms cases to be included in the sample. It gets even worse if there's non-response. So if these labs were included in the sample or included in the list and sampled, but refused to provide information, then Mary ends with a sample of 3 labs. And from these 3 labs, this is the estimate she gets. And so what I'm trying to say here is that some of these errors are really spectacularly effective in screwing you over. In particular, things that have to do with non-response, when the non-response is what we call non-ignorable, and we'll talk about that later on, then the results you get from your sample can be dramatically biased. All right. So that is as a means to introducing you to some of the stuff we're going to talk about. I wonder whether, does anybody have any questions or comments, or before I move to talking, whatever happened here, before I move to talking about terminology and definitions. All right. So let me get on to terminology and definitions then. So we've already mentioned several things. So I've been talking about a target population or a relevant population. This is simply the collection of items you wish to describe. You define the population. So the population could be a seizure of baggies that contain white powder, or it could be all undocumented migrants who cross without detection through the southern border between points of entry. So between Mexico and the United States, between points of entry, what's a population of undocumented migrants that manage to cross undetected? Or you might want to know what is the universe or the population of pattern elements in the outsoles of the shoes that are worn in Ames, Iowa in 2021. So the population can be absolutely anything, and it depends on what it is that you're interested in studying. So the sample is a subset of the items in the population. So in the case of the seizure with baggies containing white powder, the sample may be 100 baggies that are drawn from that seizure. In the case of undocumented migrants who were detained, in the case of the migrants that crossed, and this is a tough one, right? Because the population here is the people that cross without being detected. And so how are we going to take a sample from those? That's going to be a really hard one. Well, we might take a proxy sample. We might say, I'm going to look at all the undocumented migrants that actually got caught when they were trying to cross, let's say, between January and April. And then I'll see whether I can do some statistical modeling to try to estimate the number that crossed without getting caught during the same period, for example. In the case where the population is the type of pattern elements you might observe in shoes that are worn by people in Ames during last year, you might, for example, collect a sample by deploying scanners around town and taking images of the bottom of the shoes of the people that step on those scanners, let's say during a week in summer, a week in winter, and a week in fall, and a week in in spring, just to make sure you cover all the seasons of the year. So there's many populations that are non-standard, that will require creative sampling methods, but at the end of the day, a sample is just going to be some sort of a subset of the items in the population that you want to study. And we talked about samples as in the major two types of sample. One of them is what we call probability samples, and the other ones are what we call non-probability samples. And again, we'll talk about those now. So I'll say something about non-probability samples, and then I won't say a whole lot more, because as a statistician, I really don't find them very useful. Sometimes they are unavoidable, but if you really want to say something about a population, you're going to have to use a probability sampling approach. So non-probability sampling methods are not used in science very much, except in the social sciences and in qualitative research. So sometimes there's some cases where collecting a random sample is really not practical. Here's a case. The population of interest is not well defined. So for example, users of illegal drugs or undocumented persons. I don't really have a list of all the undocumented persons that live in the United States from which I could go and draw a sample. I mean, there is no such list. This is not a group of people that wants to be identified. And so what should I do in this particular case if I want to get a sample of undocumented persons in the United States? I might use a method, for example, that's called snowball sampling. So I might, or network sampling. I might, for example, find one or two undocumented people and then ask them to introduce me to their friends or to their circle of acquaintances or what have you. And so I may end up assembling a sample that way. That's not a random sample. I don't know how representative that sample is of the population of undocumented persons, but it's a way to get a sample. Another situation where non-random samples may be useful is when you have something that is either very costly to measure or where the person doing the measurements is put at risk. So for example, suppose that you want to be measuring the concentration of some radioactive compound at a site. That's not only very expensive to measure, it's also, the people that are making the measurements are put at risk. And so this is one case where you might want to think about some specific sites in which you want to go get a measurement, and those might not necessarily be randomly selected. And so the big limitation, of course, with this non-random sampling approaches is that they don't allow us to say anything about the population. They just allow us to say something about the sample elements we have drawn. So I can do whatever I want to do with the measurements I obtain from the sample, but that's as far as I can go. I cannot say anything about the population of radioactive sites or the population of undocumented persons. That's a big limitation, actually. So there's any number of non-random sampling methods. You will find them everywhere. So the convenience sampling is one approach. So let's suppose that this happens when you select elements from a population that is handy. So let's say I want to say something about guns, and instead of in Chicago, and instead of getting a sample of guns in Chicago, I go to my own armory and I sample guns from my own armory. Well, that might be convenient, but it's not necessarily representative of the firearms that are in use in Chicago. Or let's suppose I have this gigantic pile of baggies that contain some sort of powder. And instead of mixing this gigantic pile and grabbing, whoops, sorry. Sorry about that. instead of grabbing baggies from the middle of the pile and the bottom of the pile and all over the pile, let's suppose I grab the ones that are closest to me at the top of the pile. That's a sample of convenience, and that's not a good sample. We talked about snowball or network sampling. This is when I have a population that is actively hiding from me. And so what I would do here is I might find one or two members and then use their contacts to continue building the sample. And then what's called purposive sampling. This is when I call it perverse sampling. I think this is really a bad way to go. This is where you select sample elements using some criterion. And this might sometimes be useful when the attribute is expensive to measure or when the risk to subjects is very high. So here's an example. Let's suppose that I have pressure sensitive adhesives and I want to analyze them using AFM. And as you know, it takes a lifetime to get one of these measurements. And so I might then be very purposive about which types of adhesives I'm going to include in my sample, because I only have time to do 5 analyses. And so I want to get as much information as I possibly can. So the problem, there's many problems with non-random sampling. One problem, of course, is that you end up, or you have a pretty good risk of ending with a biased sample. Here's a very simple example. Let's suppose, imagine this was the population of baggies, and this is the top of the pile, and this is the rest of the pile of baggies. And I conveniently only sample the first 2 layers of the pile. I don't get my hand into the deeper layers of that pile. Well, what would happen is that in that particular case, I would be ending with a sample that looks like this, that, for example, doesn't include any yellow or orange baggies. So that's already a pretty bad sample. And it includes, so a reasonably large, so it includes 1 gray baggie, which looks like a big percentage of the baggies in this particular sample, but it is a minute little percentage of the baggies in the entire population. So gray would be overrepresented, and yellow and orange would be underrepresented, and so on and so forth. So that's what can happen when your sample is not random. Okay. So I don't think I'm going to say a whole lot more about non-random sampling. I'm going to then move on to talk about probability sampling for, what time is it? For the rest of the time. And before I go there, can you, Anthony, my watch is crazy. Can you please tell me when we get to close to half of the period so that we can do a little break?
We are 10 minutes away from 1 o'clock, which is the halfway point.
Okay, let's do a 10-minute then.
Right now?
No, sorry. Let me go another 10 minutes and then we'll do 5 minutes.
Okay, sounds great.
All right, let me know. Okay, so probability sampling. So probability sampling, like I have already said many times, allows us to say something about the population from which the sample was drawn. And so that's a big plus of probability sampling. There's any number of methods to draw a probability sample or a random sample from a population. We're going to talk about 3 in particular. We'll do a dive into these 3 and mention a few others. The 3 most common methods would be simple random sampling, stratified sampling, or cluster sampling. And then, of course, you can combine these. There's many other methods. These are the bread and butter of sampling. And the other thing that we can distinguish is whether sampling is with replacement or without replacement. With replacement means I stick my hand into the population, draw an item from that population, take a measurement on that item, and then return the item to the population. And then repeat this, draw another item from the population, take a measurement, throw the item back into the population. So when I sample with replacement, of course, any one item has a chance of being selected more than once. So any one item can appear more than once in my sample. Most typical is sampling without replacement, where I stick my hand into a population, I draw a sample of whatever size, and I don't throw the items back into the population. So once an item has been drawn out of the population into the sample, that's it. That item cannot be sampled again because that item is no longer in the population. And this is going to have an impact on how we calculate sample sizes next Friday and on other quantities. And when the population is very large, the population from which I'm drawing my sample is very large, we often assume that we're sampling with replacement, even though we're not. And the reason we do that is that statistically, everything gets easier. When we have a small or relatively small population and we sample without replacement, then we have to worry about this thing called small population correction, I think it's called. And so we don't if the population from which we sample is large. And so in that particular case, we wrongly assume, but without consequences, that the sampling is with replacement. All right. So, oh my God, I've said this so many times. So, sorry about that. So, again, the main difference between probability and non-probability sample is that in the former, I know the probability of selection of the sample items, and in the latter, I don't. And so in non-probability sample, like I said, we don't even know sometimes what the size of the population from which we are sampling is. Let me go back to the case of, undocumented migrants. We don't know how many there are. We don't really know the size of that population. And so we really don't know what the probability of selection for any one person would be if we had a sample of such people. And so only probability samples will allow us to make inference about the population, and non-random sampling will not. So here's a simple example. Suppose I pick suppose I'm wanting to measure something at the county level in the state of Iowa. There's 99 counties in Iowa. And one thing about the counties in Iowa is that they're very different from a demographic point of view. So some counties have a large Hispanic, Native American population. Some counties are lily white, very few minorities. And so let's suppose that I pick 4 counties in Iowa purposely. And what I do is I pick one with very few minorities, I pick one with very large proportion of minorities, and then I pick 2 in between. Well, that is purposive sampling. And whatever it is that I'm measuring at the county level can be generalized only to those 4 counties. There's nothing I can say about the other 95 counties in Iowa that were not included in that purposive sample. On the other hand, if I pick 4 counties at random from the 99 counties in Iowa and then do the exact same thing, whatever, take the same measurements, whatever I find, I can say a randomly sampled county in Iowa will have these attributes, because those 4 counties randomly selected from the group of 99 counties, in some will be representative, if I did this right, will be representative of the 99 counties in Iowa. So you must know, if you're looking at somebody else's data, you're reading a paper, you're reading a standard, you're doing whatever, you really have to ask yourself these questions. How were these data collected? And so before you decide whether the data that you're looking at are relevant to answer your question, you have to go back and see and ask yourselves, was this a purposive sample? Was this a random sample? Was the sample large enough? So these are important questions that you have to ask before you believe anybody's paper or before you believe anybody's testimony or before you believe anybody's findings. Okay, so here's more terminology. The inference, we've already talked about this. Inference is simply means learning. And so this is just deriving information about the population using the measurements that you obtain from the items in your sample. The sampling frame is a term you're going to run into. This is simply the listing, the actual listing of the population items. So the sampling frame in the case of undocumented people in the United States cannot be constructed because I don't have a listing of all the undocumented individuals in the United States. But the sampling frame of a seizure of baggies containing white powder simply would be a listing of every baggie in that seizure. And so in order for me to draw a random sample, ideally, I would number those baggies from 1 to 10,000, let's say, and that would be my sampling frame. The undercoverage occurs when the sampling frame is not complete. And overcoverage occurs when the sampling frame includes items that don't belong in that population, that are from some other population and somehow got thrown into my list. Enumeration simply means the listing of each item in the frame. So if when I say I enumerate the items in a frame, what I mean is I am labeling those items from 1 to population size, whatever the number of items in the population might be. Coverage, we talked about coverage, is whether the frame excludes or not important segments of the population, or whether it includes segments it shouldn't be including. So in the example for the seizure of baggies, let's suppose that some of the baggies have powder in them, but some of the baggies have tablets in them. And I only sample from the ones that have powder. Well, I am undercovering, right? Because I am excluding all the baggies with tablets from my listing, and therefore I have no way of putting them into the sample, including them into my sample. And strata is another term we're going to be using. Strata simply means subgroups in the population. So a stratum is a subgroup in the population that is homogeneous in some way. So for example, in this particular example where I had some baggies with powder and some baggies with tablets, I would have 2 strata in this population. The strata that includes all the baggies with powder, and the stratum that includes all the baggies with powder, and the stratum that includes all the baggies with tablets. And so it is, so stratification or dividing the population into strata is important when the population from which you want to draw a sample is heterogeneous in some way. It could be a, this is a pretty obvious way, some are tablets and some are powder. But suppose that every baggie contained powder, but some of the baggies were blue and some of the baggies were pink. I don't have any idea whether that is related to the content of the baggies. So in that particular case, I would still have to stratify the population into the blue baggies and the pink baggies because I'm not sure whether that particular characteristic is associated with the variable of interest for me. All right. We talked a little bit about sampling error already, and it's the error or the deviation from the true population value that arises because I am working with a sample and not with the entire population. So what we call sampling error is really not an error, it's not a mistake. Rather, we think of it as uncertainty or variability. So the fact that I am taking a measurement on a sample of items in the population simply says that those measurements are going to be an approximation to the to the quantity I might have computed if I had had the same measurement, but for every item in the population. And so here's, let's see, there's something in the Q&A. Oh, yes, sorry. So Laurel is asking whether the handouts are available. And yes, the slides that I'm using are available. I don't know if, okay, not Anthony's fault, because I sent the slides to Anthony about 10 minutes before we got started. But if Anthony hasn't sent the slides yet, he will pretty soon to everybody that's participating. All right, so let's suppose that I have a population and the population is a shipment with 10,000 white tablets. And I want to know what the average weight of some substance in those tablets might be. And so in order to know exactly what that average weight would be, I would have to analyze all 10,000 tablets. But instead, I analyze a sample that includes 100 tablets from that population. I can estimate the average weight of that particular substance on those 100 tablets, but that's going to have a margin of error. So what I am going to be reporting is the average weight in the sample, plus minus a margin of error. And that margin of error is what we call the sampling variability, or is related to this sampling variability. And this margin of error, of course, I can control. That's great. And I can control it in many ways. One way, for example, is by increasing my sample size. So determining the sample size. So one way to determine the sample size I need is to first decide how much of a margin of error I'm willing to live with. And then, given that margin of error, figure out how large a sample I have to have in order for my margin of error not to exceed that, ceiling that I placed for myself. Whoops, why in the world? Oh, okay. So here's an observation. All sampling is contextual. So what is fabulous sample in one application may be a totally inadequate sample in another application. And so we'll talk about this, this issue later on as well. Is it time for a break?
You could take a break. I was trying to wait until a natural pause, which I think happens at slide 32.
Oh, okay. Let's go on then. So, okay, so after attributes of a good sample. So we've been, oh my God, I'm slow today. So we've been talking about, around the margins of what the attributes of a good sample are. So let me list a few of those. And we'll go over these in more detail in a minute. But in principle, a sample is a good sample if, first of all, it's drawn from the target population. So you didn't draw it from some other population. Second of all, is free from what we call selection bias. And we'll talk about selection bias in a minute. Second of all, items in the sample have a known probability of selection. So this is a probability sample or a random sample, a statistical sample, whatever you want to call it. Third, it has a low rate of non-response. So you actually manage to get a measurement on every item or on almost every item in your sample. And finally, has low measurement bias or measurement error. So the measurement you got is actually relatively accurate, is free from measurement error, if you will. So today we're going to be talking about the strategies to draw good samples. And so let's go through some of these terms. So what is a representative sample? A representative sample is, if you will, a microcosmos of the population from which you drew it. So it's a mini version of the population from which you drew that sample, at least in important ways. So what do I mean by that? Well, let's go back to that example where we had some pink baggies and some blue baggies in the population. Let's suppose that I know that this is just, there's no difference in the content of the baggies that has to do with the color of the baggies. And I know that because I have some other information. Well, in that case, even though the population includes pink baggies and blue baggies, and my sample, let's say, only includes pink baggies, that doesn't matter. The sample is still representative because the color of the baggie is not an important attribute of the baggie. If I don't know whether the color is associated with the content of the baggie, of course, I have to have both blue and pink baggies for the sample to be representative. Otherwise, it wouldn't be. And so the problem with representation is that if you have a non-representative sample, then that will result in a biased inference, and biased inferences about the population because the sample is simply not representing the population. Selection bias occurs when some items in the population are either overrepresented or underrepresented in the population. A typical example of selection bias occurs when, for example, you have a study with human participants and you allow participants to self-select. So when people call for volunteers, let's say I'm conducting a study and I send out a note to all forensic practitioners and I say, can you please volunteer for the study? That is an example of selection bias because the people that volunteer to participate in studies are typically different in important ways from people that do not volunteer to participate in studies. For example, people that volunteer to participate may be less busy in their daily work than people that do not volunteer. Or they may be more confident in their ability to respond to the questions than people that do not volunteer. Or they may be more actively involved in the community than people that do not volunteer. And all of these attributes, all of these differences may be associated to the type of answers they would provide in the study. So any study where you have self-selected or volunteer participants, you can expect selection bias to be operating in that case. Non-response is when we fail to obtain a measurement from a sampled item. And so for example, let's suppose that I have a sample of baggies that I drew from the seizure and I ran out of time or I ran out of reagent or what have you. So I only analyzed half of those baggies and the other half went without analysis. That would be 50% non-response in my particular study, and depends on the type of non-response that could or may not be a problem. So there's what we call ignorable non-response, and there's what we call non-ignorable non-response. And I think this is, okay, so that's what we're talking about here. So ignorable non-response is when the attributes of the items that were not measured are not related to the value of the measurement. So let's suppose that the baggies, so I have a random sample of baggies from a seizure, and let's suppose that I took 100 baggies out of the seizure and the 100 baggies look identical. And I analyzed only half of those and the other half I threw back into the population because I didn't have time. Well, this is probably ignorable non-response in the sense that chances are the baggies I didn't analyze are not significantly different from the ones I did analyze. And so the only problem that I have here is that instead of having a sample of size 100, I ended up with a sample of size 50. So my sampling error is going to be higher, but I will not have a biased estimate of whatever it is I am measuring. The problem comes when you have non-ignorable non-response. So this occurs when the items for which I didn't get a response are significantly different from the items for which I did get a response. So here's an example. Suppose that I want to know the backlog in the analysis of rape kits in crime labs in the United States. And so I send this questionnaire to a sample of, so you would expect that the size of the lab here is related to this. So I send a questionnaire to a sample of labs that have been stratified by size. So in my sample, I have large labs and small labs and medium labs and so on. And let's suppose that I get responses back only from the small and the medium size labs. Then you can expect that and I get no response from the large labs. So here I know that I'm going to have a bias in the estimate of the backlog because there is a difference. You know, the size of the lab matters when it comes to the backlog. And so this is an example of non-ignorable non-response. In this case, not only do I end up with a smaller sample and therefore larger sampling variability, I also introduce a bias in my estimate, and this is a big problem. So here is the typical non-response, non-ignorable non-response bias. I sent a survey, and what I find is that I get 500 responses, and people say I love responding to surveys, and only 0.2% say I toss them in the bin. Well, that's because everybody that tosses them in the bin didn't respond to your survey. And so here's a typical example of a biased response that results from non-ignorable non-response. Shall we go on? So, all right. So what I would like to finish today is I would like to go over sampling methods, and then we can talk about inference and sample sizes next time. So there's, as I said earlier, there's many forensic applications of these sampling ideas, and there's many different questions we might ask ourselves about a population. So we might ask questions, whoops, sorry. We might ask questions that have to do with a proportion of items that meet certain characteristics. So what proportion of, what proportion of messages, what proportion of images in a computer include some illicit content? That's one of the things we might ask ourselves. Or what is the total weight of something? So what's the total weight of the shipment? Or what is the total amount of dollars in some fraud investigation? What is the population size? How many baggies are there in the shipment? So these are different questions about different attributes of the population. This has to do with the frequency with which we observe some characteristic in the population. This has to do with the average weight or the average value of some attribute in the population. And this has to do with the population size. And so these are things we might wish to estimate, and we're going to be using different approaches. And in fact, different sampling approaches might be appropriate for these different questions. And this is from one of the standards, whatever your purpose, try to use a probability sample, because that allows you to estimate uncertainties and biases, maybe, and variance of estimates. So regardless of the question you have, random sampling is probably going to be the better approach. Here's a list of some of the standards, the ASTM standards that mention sampling. I am not going to go over them in detail, but I'll be happy to answer questions that anybody may have about any one of these standards. This is not an an exhaustive list. There's other ASTM publications that also mention sampling. And then there's other resources. For example, there's a United Nations guidelines for direct sampling that I find very useful. There's an EMSFI user's manual, if you wish, on how to do hypergeometric sampling. We'll talk about hypergeometric sampling next time around. And I will put all those, or I'll make sure that Anthony shares some of these documents after we're done with today for sure. Okay, so this is revisiting an earlier slide. Remember, we sample for many reasons, but the one we're going to focus on in the remaining is learning something about a population. For example, the frequency of some attribute, or the average value of some attribute, or the size of the population itself. So again, I've already said this, but I'll say it again. So even if you do not collect data yourself, and sometimes as a practitioner, you don't collect data yourself, but you will be looking at other people's data. And so you have to be able to think critically about this data and how these data were collected, and whether you should believe whatever the findings are that somebody is reporting based on those data. Okay, the value of good data. Remember the dinosaurs. Who cares about data? I know, my gut. All right, so let's start talking about probability sampling methods. And but before we go that, we'll start thinking about some notation, because we're going to start looking at a few formulas here and there, not many, but a few. And so here are some of the terms that you will often see when you read anything that's related to sampling, including the ASTM standards. The letter big N is often used to represent the population size. And oftentimes N, sometimes you don't, and it's something you want to estimate. Little n is often used to denote the sample size. So little n is something that you choose. And so we'll talk about ways to picking little n next Friday. F is sometimes used to represent what we call the sampling fraction. That simply means the fraction of the population that you're going to be including in your sample. So F is little n divided by big N. And oftentimes this F is very, very small. So oftentimes you work with very large populations and very small samples. And so F can be pretty small. Y sub I is the measurement of whatever characteristic you're interested in. That's the measurement on the ith population unit. And so I here is just an index that takes on values from 1 to capital N. So I equals 1 would be the first population unit. I equals 2 would index the second population unit, and so on. So these are non-observed values. These are values in the population. What you do observe is the little y sub I. These are the measurements on the ith sample unit. So this is the measurement of whatever variable you're interested in the ith sample unit. And again, I here is only an index, like a label. And so little y sub 1 is your first sample unit, little y sub 2 is your second sample unit. And here in the sample, I just goes up to little n, which is the number of units in your sample. Y bar we often use to denote the average of the measurements obtained from the sample unit. So if I take all the little y sub I, so y1, y2, y3, all the way to yn, I add them up and then divide by little n, that gives me y bar. That's just the sample average of the variable I'm measuring in my sample. Y bar is what we call an estimate of mu. What is mu? Mu is the average of all the measurements in the population. So if I could observe all the big Y's here, all the big Y's on all big N items in the population and average those, then the value of that average is what I'm calling mu. So mu is this unobserved estimate, unobserved average that I want to estimate. So Y bar here is going to be my estimate of mu, and estimate is a fancy word for my best guess for mu. S is the letter we use to denote standard deviation of the measurements in the sample. So for those of you that don't remember, standard deviation is simply a statistic that that reflects the variability, the range of values that I observe in the sample. So if all the little y's are close to Y bar, you know, they're all close together, then S is going to be small. If I have a huge range of values of little y in my sample, then S is going to be larger. And S is an estimate of the corresponding population quantity. And the corresponding population quantity is denoted by sigma. This is the Greek letter for S. And the same as mu, sigma here refers to the big Y sub i's. So if I could observe all the big Y sub i's and I computed the standard deviation of all those big Y sub i's, that would be this value sigma. And so S, which is based on the sample values, this is just my best guess or my estimate for sigma. Oftentimes you're going to see big X used to denote the number of positives in a population, whatever positives may be. So positives may be the number of baggies in the container that actually contain drugs. And so big N minus X would be the number of negatives. In other words, the number of baggies in the population that do not contain drugs. And again, to get X, what I would have to do is I would have to go to the entire population, look at each item one by one, and decide whether an item is positive or negative for whatever it is that I'm looking at, and count how many positives there are in the population, and that is this value big X. Unobservable unless I, of course, get to observe every item in the population. And so the corresponding sample value is little x. And so this would be the number of positives in the sample. So I have my little n items in my sample, and I look at each one of those little n items and I count how many of those little n's exhibit the trait of interest, those are the positives, or don't exhibit the trait of interest, those would be the negatives. Finally, little p here would be the proportion of positive items in the sample. So how do I compute little p? Little p is simply little x divided by little n. So how many of my sample units exhibit the trait of interest? And as you may by now guess, little p is a good guess or an estimate of pi, which is typically used to denote the proportion of positive items in a population. And if I could observe all the items in a population, pi would simply be computed as big X divided by big N. So all the quantities that are sample-based, all the quantities that I can actually obtain by looking at the items in my sample, all of those are called statistics. So Y bar is a statistic, and S is a statistic, and little x is a statistic, and P is a statistic. And those are estimates or guesses of what's called population parameters. Population parameters in this case would be mu and sigma and big X and pi. Those are summaries of the population, attributes that I cannot observe. I can take a guess by looking at the corresponding values in the sample. So when I talk about a statistic, I mean something that I compute using sample items. When I talk about a parameter, I mean an attribute of the population that I am going to try to learn something about from the sample. So again, let's talk about sampling. We already said this before I get into simple random sampling. So sampling with replacement or without replacement. We mentioned this before. So sampling with replacement is something that I rarely do. I select an item from the population. I obtain the measure. Oh, this should be little y. Shame on me. This is not good. This should be little y. I obtain the measurement little y. I return the item to the population. And so the consequence of sampling with replacement is that each population item can appear in the sample more than once. And the other consequence is that the selection probability for any item on any round of sampling is the same, regardless of what is already included in my sample. So let's suppose that I have 10 items in the population and I stick my hand into the population bag and I sample one of those population items. And if I do this strictly at random, each item has a chance 1/10 of being selected. I take that item and let's suppose that was item number 7. And I write the y correspond, the measurement corresponding to item number 7. I throw it back. Well, all 10 items once again have a chance 1/10 of being selected as the second sample item. Regardless of the fact that I already have number 7 here, because I threw number 7 back in. And so the probability of selection of any item doesn't change when I have sampling with replacement. This is not a typical sampling approach, but unfortunately, it's the one that makes the statistics easiest. And so when we have very large populations, we'll pretend like we're sampling with replacement, even if we're not, because the statistics get easier, the calculations get easier, and the results do not change much. What we normally do is sample without replacement. And so what do we normally do? We stick a hand into the population, we select the first item, we measure the variable, and I set that item aside and select the next item, and so on and so forth. The consequence, of course, is that after the first item is selected, the rest of the items, the probability of selection for the rest of the items changes. Because let's suppose I start with a population of size n. Now, once I selected item number 1, there's only n-1 items left in the population from which I can select item number 2. And so the probability of selection of each population unit after the first depends on how many other units and of which type I have already sampled. And this is what makes calculations complicated when you have sampling with replacement, because every time you draw a sample from the population, your population changes. And so it gets hard to keep track of the probability of selection of any unit after the first unit was selected. Okay, so again, like I said, what did I do here? Sorry. When n is large, it really doesn't matter. When the population is large, it really doesn't matter. Using the sample measurements. So typically, we're going to have a sample of measurements that we call little y1, little y2, all the way to little yn. And we're going to be computing the sample statistics from these sample measurements. And The statistics could be the sample mean, the sample standard deviation, the proportion of some attribute in the sample, whatever it is. And like we said, these statistics are what we call point estimates of the corresponding population parameters or population quantities. So Y bar is going to be a point estimate of the population mean mu. S is a point estimate of the population standard deviation sigma, and P is a point estimate of the population proportion pi of some attribute. And the way we compute these sample statistics and the type of sample we work with is going to determine the properties of these sample statistics or sample estimates. And by properties, I will talk about properties, but what I mean is how good are these guesses of the corresponding population quantities, essentially. So let's start with simple random sampling, which is the easiest and simplest approach to sampling. So what you have is a population of size big N, and what we want to draw is a sample of size little n. And simple random sampling simply means, sorry for the pun, that every possible sample of size little n from this population has an equal probability of selection. So imagine I have this gigantic bag with a population of size big N, and I stick my hand and I randomly grab little n items from that population. Any set of size little n under this sampling approach has equal probability of selection. So if I have n big items in the population, there are n to the little n possible samples of size n. It turns out to be a humongous number. We'll see that in a minute. So essentially what this means is that each possible sample that I could draw from this population of size equal to little n has 1 over n to the little n probability of selection. This happens to be true when n is large, when the population from which I'm drawing the sample is large, and when sampling is done with replacement. So here's an example. So if I am drawing a sample of size 1, then the number of all possible samples that I could draw from the population is just the size of the population. If n is bigger than 1, if my sample is bigger than 1, and sampling is with replacement, then computing the number of possible samples is a little harder. So suppose that I have a very small population. This is just for illustration. I have a population and the items in the population have labels A, B, C, D, and E. And so I have 5, big N is equal to 5. And I want to draw a sample of size 2. So what are the possible samples I could draw? I could actually enumerate all possible samples. Well, if I am drawing with replacement, one possible sample is I draw item A, and the first item I sample is A, throw it back. And the second item I sample is also A. Or maybe I drew A, I threw it back, and then I drew B. Or maybe I drew A, and then I threw it back, and I drew C, and so on and so forth. You can actually enumerate all the samples that you could get. And if you do that, you'll find that there's 25 different samples, which in fact corresponds to big N to the little n. And so in general, like we said, the number of possible samples you can draw when you have sampling with replacement is n to the big N. And so if I have a pretty small population of size 100, and I want to draw samples of size 4, let's say, it turns out there's about 100 million possible different samples of size 4 that I could select. It really gets pretty high pretty fast. If I am sample without replacement, however, then it gets a little harder to count, but let's see how we would do that. So if I am sampling without replacement, and let's suppose I have the exact same population that has 5 items, A, B, C, D, and E. And let's suppose that the first item I draw is B. So now I put B aside. The second row can no longer be B. It can only be A, C, D, or E, because B is no longer in the population. And so I can still enumerate all the samples I could get. So the samples I could get, the same that we had before, except that now I don't have AA, I don't have BB, CC, DD, EE, and AB is the same as BA, because you know, I can list them, so I could get A first and B second, or I could get A first and C second, and so on and so forth. And there's 10 possible combinations, because whether I get A first or B second, or B first and A second, will count as one, because at the end of the day, that's just a sample. It's the same sample. And so much fewer. I can only get 10 instead of 25 samples when I sample without replacement. And so how do I count? So how many different samples can I draw? And we've already said that in this particular example, I have 10 of them. The formula, there's a formula for this, and the formula is the following. The number of possible samples of size little n from a population of size n when I do not replace is this thing that we have here is we call it big N choose little n. And the way you calculate this thing is as I have here. So what I have in the numerator is n factorial, and in the denominator is little n factorial n minus multiplied by big N minus little n factorial. What's a factorial? Well, if big N is 5, factorial is just multiplying down from 5 all the way to n. So 5 times 4 times 3 times 2 times 1. That is 5 factorial. So that's what I have in the numerator. Then little n factorial is just 2 all the way down to 1. So 2 times 1. And then n minus n, so 5 minus 2 factorial, that's 3 factorial, right? N minus n is 3. 3 factorial is just 3 times 2 times 1. And if you do this calculation, you get 10. Now, if I have 100 elements in my population and I want to draw samples of size 4, how many possible samples can I draw? Well, I could draw, so in the numerator, I would have the multiplication from 100 all the way down to 1. So 100 times 99 times 98 times 97, blah, 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 blah. And then in the denominator, I have little n, which is 4. So I have 4 times 3 times 2 times 1 times big N minus little n factorial. So that's 96 factorial. So 96 times 95, blah, blah, blah. If you do this calculation, it turns out you end up with almost 4 million. So 3.9 million possible samples. Compare this to the almost 100 million I had when I used sampling with replacement. And you can see that when you sample without replacement, the number of possible different samples you can get is a whole lot smaller than when you sample with replacement. It's still enormous, but it's a whole lot smaller. All right. So that's the number of samples you can get. Now so that allows you to compute the probability of observing a certain sample. Okay, so what are the mechanics? How do you actually implement simple random sampling? Well, ideally you have a population that has been enumerated or labeled. And so let's suppose that your items in the population are labeled from 1 to big N. And so if you wish to draw a sample of size little n, you typically would use a random, you let the computer randomly select little n values from the set of labels between 1 and big N. So, and then you would just go and pick those specific items. Or you could use something called systematic selection, in which you would calculate a value k, where k is just like a step size. So this would be the population size divided by little n. And then you would pick a random start, let's say a random value between 1 and k. And then from there on, you would systematically choose every kth item thereafter. So this is still random because you start from a random place. And so every subsequent pick is still random. Let's see, there's something on the question. Oh, okay. All right. So there's the same type of methodology will afterwards apply to other sampling methods. And then there's other approaches, but these are two very commonly used approaches. So this is where I want to go. So here's a visual for what a random sample might be. So here's the population, and there's 12 individuals in this population, and you have enumerated them between 1 and 12. And so if you want a sample of size 4, you would randomly pick 4 numbers between 1 and 12. And in this particular case, let's suppose you pick 2, 5, 8, and 11. That would be your sample of size 4 from this population. So when is a good, so the one advantage is of simple random sampling is that it's so easy to use, and the calculations that we do with the items in the sample are very simple too. And so, but unfortunately, it's not a very efficient sampling approach in some cases. So simple random sampling is a very good choice when you have a population that's more or less homogeneous. So if you happen to have a shipment of, let's say, 10,000 identical looking teddy bears all wrapped individually, some of which you think may carry drugs, you know, using simple random sampling in this case is a good idea because you have a pretty homogeneous population. You can also use simple random sampling in a heterogeneous population, but in this case, it's not a very efficient way because in order for the different population subgroups to be represented in your simple random sample, you would have to have a very large sample. So when the population is heterogeneous and some types of items in the population appear in small frequency, some items are rare in the population, then simple random sampling is really a bad way to go because unless your sample is gigantic, those rare items are likely to not be represented in your sample. And so an example would be, imagine you want to look at the shoes that are sold in Ames to look at the frequency of different patterns. So how many of the shoes, athletic shoes, let's say, have little squiggly lines in the bottom? How many have little bow looking things in the bottom? How many have, you know, circles and as part of the pattern? Well, if there's some patterns that are pretty rare or combinations of patterns that are pretty rare, unless you obtain a very large sample of shoes, you would probably not observe those patterns in your sample. So in these cases, you're better off using some sort of stratification to guarantee that all of the subgroups in your population will be represented in the sample. So that's where we're going now, stratified sampling. So what is stratified sampling? Well, stratified sampling is what we want to use when the population from which we draw the sample is not homogeneous. In other words, that population includes different types of items. Let's say the population of shoes would include different shoe brands. And it's not a big issue if all the different types of items are more or less equally represented in the population. The issue arises when some of those types are more abundant than others. So when the population is not only heterogeneous, but also those subgroups appear in very different frequency in the population. So in that case, a much more efficient strategy is to stratify. And what do I mean by efficient? I mean, you can get away with a smaller sample and still maintain the same accuracy. We'll talk about that later on. And so the idea here is to look at your population, stratify, so create these different subgroups of items that are different. Each stratum or each one of these subgroups is now going to be homogeneous because it's only going to include items of the same type. And what you do later is you typically use simple random sampling within each stratum to construct your sample. So you first stratify, and then oftentimes you use simple random sampling within each stratum. And that way you guarantee that every stratum or every subgroup is going to be represented in your sample. Of course, the question you ask now is how many items from each one of these subgroups do I need to include in my sample? And that is going to depend on the type of question you're asking from the population. I will talk about that in a minute. But one consequence may be that the items in the population no longer have an equal probability of selection. Suppose that I have a population with 10 items, and let's suppose that 8 are of one kind and 2 are of a different kind. And I desperately want to have, so, you know, in the population, 0.8 probability, or 80% of my items are of kind 1 and 20% of the items are of kind 2. And I want a sample of size 5. And I desperately want to have items of kind 2. I want them represented in the sample. So one possibility would be for me to say, I'm going to pick both of the items of size of type 2, both of them. I'm going to put them in the sample. And then I'm going to get 3 at random from the items of size of type 1. Well, now the probability of selection is completely different because the items of size type 1 had a probability of selection equal to what? 3 divided by 8, because I picked 3 from among 8. But the items of size of type 2 had 100% probability of selection because I picked both of those. And so that I have to keep in mind when I compute quantities using my sample items. Because if I were to compute, for example, the population average using that sample, I would get a bias because my sample is not representative of the population. In my sample, 2/5 of the items are of type 2, whereas in the population, only 2/10 of the sample are of type 2. And so we'll go over that in more detail later, but that's one consequence of stratified sampling, that you may end up with a sample that's no longer representative of the population. So when you look at anything that has to do with stratification, you will often see people use the letter H, little h, to indicate the stratum. So if in a shipment, for example, I have vials, vials with a clear liquid. I also have red tablets, and I also have small white pills. Then I have 3 strata in this population. And so the H here would take on values 1, 2, or 3. So when H is 1, for example, I'm talking about the clear liquid vials. And when H is 3, I'm talking about the small white pills. And N sub H is going to be the number of items in the population that are included in each one of the strata. So the N sub H is the number of items in the H stratum. So once I have the strata defined and I have enumerated the number of items in each one of those strata, then how do I sample? Well, let's suppose I draw random samples from within each of the strata. So I may draw, for example, little n1 items from stratum 1 that had big n1 items in it to begin with. And then I might draw at random little n2 items from stratum number 2 that had a total of big n2 items in it. And so at the end of the day, if I do this for all H strata in my population, then the sample size I end up with is just the sample, is the sum of the within stratum sample sizes. So it would be little n1 plus little n2 all the way to little nh. I add them all up, and that gives me my sample size. And so the question is, how do I decide what's n1, what's little n2, what's little nh? So suppose that I already know what n is. I have already decided what my overall sample size is going to be. How do I distribute that overall sample size among the H strata? And there's different ways to do this. Hello. And one way is to use something called proportional sampling, or PS, where what I do is I take a number of observations, little n sub h, that is proportional to big N sub h. So let's suppose I go back to, let's suppose that I have a population of size 100. And let's suppose that 80% of the items are in one stratum and 20% of the items are in the other stratum. So 80 items in one, 20 items in the other. And I want a sample of size 10. Proportional sampling here would then be pick 8 items from stratum 1 and pick 2 items from stratum 2. And so the proportion, I am preserving the proportion of the 2 types of items in the sample that I had in the population. And so this is the best approach if what I want to estimate is the overall population mean, for example. And the reason is that the sample that is obtained using proportional sampling is representative of the population. It's like a mini population. The items are represented in the 2 types of items are represented in the same proportion in the sample as in the population. Another possibility is to say, forget about the proportions. What I'm going to do is I'm going to distribute my sample equally, my sample size equally among all the strata. So what I'm going to pick is that from any one stratum, I'm going to pick n divided by the number of strata. So this is fine if what I want to estimate is each stratum mean. Not necessarily the overall population mean, but I want to be able to estimate the mean of what I'm measuring in each one of the strata. And then there's a compromise. If what I want to do is both get a reasonable estimate of the strata level means and of the population level mean, and that compromise is to take the sample size in the H stratum to be proportional, not to the size of the stratum, but to the square root of the size of the stratum. And there's any number of things in between, but these are the 3 most common approaches to distribute the overall sample size among the strata. So here's what we might have. So here you have, let's say 4 strata, each one contains 3 items. And what I would do is I would, this is my entire population. So what I would do is I would randomly sample from within each one of the strata. And in this particular case, let's suppose, because the 3 strata have the same size, it really doesn't matter what I do, I would end up picking equal number of observations from each one of the 3. So I pick 1 from stratum 1, and then I pick 3 from stratum 2, and then I pick 2 from stratum 3, and 1 from 4, for example. Something related to stratified sampling is what's called quota sampling. And quota sampling is similar, except that we use it when we don't really have a good idea of the size of each strata in the population. So we don't have a good enumeration, and we might only know the size of each stratum approximately. And so in this particular case, we might ask, as a sampler, I might say, I'm just going to go into each one of the strata and pick a sample of convenience from each stratum using this approximate stratum sizes. And this actually, even though it sounds reasonable, it can result in huge biases. And there's one famous example in history here, which is the election of Dewey versus Truman. None of us are old, at least I'm not old enough to remember this, but if you study statistics, you always get this one example. So this is where everybody thought that Dewey was going to defeat Truman in the presidential election back in 19, whatever it was, 50 something, I think it was. And what happened was that actually Truman trounced Dewey. And how did that happen? Well, it happened because the polls at the time, this was a Gallup organization, really screwed up. What they did is they had a bunch of people that went out to collect data. And what they told them was, you need to interview 1,000 people. And the 1,000 people you interview, it has to be, actually I should say, each pollster was supposed to interview, let's say 100 people. And the only thing they told the pollsters is, among those 100 people, you better have 48 women and 52 men. And you have to have so many of this age range and so many of this other age range and so many of this. And so what these pollsters then did is, instead of randomly selecting the women and the men and the age groups and so on from each group, they used a convenience sample from each group. So I had to contact 48 women. Well, I might call all my friends that are women and ask them, how are you going to vote? And so that was they used this quota sampling without random selection, and that's how they got into big trouble. The last thing I want to cover today is cluster sampling. And cluster sampling is another similar type of, it's another type of sampling that you might encounter often. And this is kind of similar to stratified sampling in that you divide your population into groups and then sample within these groups, except that the groups that you divide the population into, which we call clusters, need not be homogeneous. And so in cluster sampling, what we do is we take the population and divide it into small chunks. And these small chunks may be very heterogeneous. And what we do typically is, instead of sampling items within the clusters, what we do is we sample the clusters. And so if I have 10 clusters in a population, I might sample 2 of those. And then within each one of those clusters, I will take a measurement on every item in the cluster. And so this is commonly used in population surveys. And one typical cluster might be a city block. And so what people will do if they're conducting a population survey, let's say in whatever, Des Moines, they will have a list of all the city blocks in Des Moines. Then they will pick a few of these city blocks in some way, perhaps at random. And then let's suppose they pick 50 city blocks. What they will do is they will go to each household in those 50 blocks and ask whatever survey question they want to ask. So how does this apply in forensic? So here's an example. So we might have 6 clusters. So the population is here and we might have 6 clusters. And what we do is we pick 2 clusters at random. And so let's suppose that we pick this cluster and this cluster. So in a sample, we include all items in these 2 clusters. This would be the sample. And so this is the visual of a difference between stratified sampling and cluster sampling. In stratified sampling, the groups are homogeneous. And so you will sample within the groups. And so you might get this red guy and this red guy, and then this blue, and this blue. And so in your sample, you're going to have some red and some blue. In cluster sampling, you might divide your population into groups that are not necessarily homogeneous. And so you might end up with this clusters, and you might sample this cluster and this cluster. And so at the end of the day, you're also going to have blue and red individuals in your sample, but the way you selected them is completely different. And the way you do your calculations of, the way you estimate population quantities is also going to be different. So you have to know how the sample was selected. Here's an application of cluster sampling in, let's say, that might be, I was trying to think of a forensics application of cluster sampling, and I came up with this one, which I don't know if it's good or not. But let's suppose that you are a customs inspector in the port of LA, humongous port. And let's suppose that 30 container ships arrived in the port last week. And let's suppose that each container ship carries about 2,000 containers each. So you have a ton of containers that you could inspect, but obviously you're not going to inspect every container. So what you could say is the following. Suppose that each ship is a cluster. So we have 30 clusters in this population, the population of all ships that arrived in LA last week. And I am going to select C clusters. This would be ships at randomly, and then open every container in those ships. That would be one example of cluster sampling. Another possibility is combining things. So let's suppose that I select the ships. So I do this clustering at the first step, and I select a bunch of ships, a bunch of clusters. And then instead of looking at every container in the ships, I could draw a random sample of containers that I will open on each ship. That's also okay. Or I could stratify the containers in each one of those ships, let's say by port of origin. Let's suppose that, the ships stop in, they start in China, and then they stop in Singapore, and then they stop in India, and then they stop in whatever before they arrive in LA. Then I could stratify the containers by port of origin, and then sample randomly within those strata. So you can actually combine any of these sampling approaches. The more stages that you have in the process you use to collect your sample, the harder it gets to compute the probability of selection of any one item, the probability that any one item will end up in your sample. But it can be done as long as you keep track. And so these two that I mentioned below are examples of what we would call multi-stage or nested sampling. And when you have multi-stage sampling, you start talking about sampling units in terms of primary sampling units, secondary sampling units, tertiary sampling units, etc. So in this example, the ship would be the primary sampling unit. And then in the easiest case, the containers within ships might be the secondary sampling units. Or let's say that the containers are full of boxes, and you sample boxes within containers. That would be a tertiary sampling unit, would be the boxes. So, I mean, you could get a PhD in sampling methods. And so I'm not going to go further than that here, but we're going to see examples and calculations using all these methods. So now I do promise that I'm finishing up. So oh God, I went over time already. Did we lose half of the participants? Well, let me finish this, and this will be fast. So there's many other special approaches to sample. There's specialized sampling approaches, like, for example, area sampling. Let's suppose that you want to sample a small geographic areas like plots in a larger area. Typically, to do this, you might rely on aerial photos or satellite images or maps. And an example might be you want to know whether there's marijuana plants mixed in with regular vegetation in a remote 100-acre farm. Instead of looking at all 100 acres, 100,000 acres, you might sample small sections of this farm and look at the plants in that section. Bulk or composite sampling, this is pretty useful and is used pretty often. This is often used for monitoring and surveillance. Let's suppose that, essentially what this means is I take a sample of size 100 from some population, and instead of analyzing all 100 individual samples, what I'm going to do is I'm going to mix them up. So out of the 100 samples, let's suppose I make 10. So I take 10 of my samples at random, I mix up all the material, and then I analyze that. Instead of analyzing 100 samples, I only have to carry out 10 analysis on the 10 composite samples. And this is pretty good. For example, this is something that is used for early detection, and this was used for early detection of COVID on college campuses. What they did is they would analyze a sample of the wastewater from a building, a dorm building. So there might have been 300 rooms in this dorm, and if there was no evidence of COVID, then in the wastewater, they would be happy that there's nobody has COVID in this particular building, instead of testing each individual student. And so this is just a visual for that. So this is a visual for area sampling. When you have just random sampling of an area, these might be the locations at which you obtain a sample. If you are stratifying, let's say that this yellow area is different from this orange area, you might want to make sure you have a few, sample points in each one of the two different types of area. And this would be a systematic sample. So you start in some random location, and then you go a specific distance in a grid, for example. Or you could do what's called line transects, in which case you would decide on, you would just start on some point and then follow a line and get samples along this line. And you can do this at random or stratified or in a systematic way. And the same with these quadrats, where instead of taking points where you take a measurement, you look at little sub areas where you take your measurements. So here's what's coming next. What we're going to be talking about is once we have my sample, what do I do with my sample values? And in particular, how do I decide on a sample size? And, we will address questions such as what's the proportion of baggies that contain cocaine in the seizure, or what's the average dollar value of each illegal transaction stored in a server, or how many firearms in a contraband shipment of 5,000 crates. So these are the type of questions that we're going to be answering next time. So this is where I'm going to stop. I apologize for going 17 minutes over time. And I thank you for sticking with me. All right, thank you guys. And I'll see you next time, I guess.
I want to thank you for sharing all of your valuable input and this education for us so far. We have 2 more sessions to go, and we look forward to those. Thank you all for joining us. We hope you have a great day.